And a good way of understanding all this is just to kind of think about what happens with functions in ordinary math. Okay, so let's maybe do a little bit of a trip down memory lane. Let's see where I can find a spot to write this out at. Let's say, and this will be an example, let f of x equal 3x plus 2. And I'm going to send you on a tiny mission here. I'm going to say, okay, find f of -1. Okay, would you mind taking a moment to calculate f of -1?
It's -1.
-1. You got it. Now, how did you find f of -1? What did you do?
I put -1 in the equation. Everywhere we have x, we put in -1. Which we
Yep.
get -3 plus 2 is equal to -1.
Yep, you got it. So basically, the way this works is f of -1 is equal to -1, since 3 times -1 plus 2 equals -3 plus 2 equals -1. Now, linear transformations, which we'll get to, sort of work in a similar way, except we don't use the mixture of numbers like this, where we have 3 times the vector x and then add 2. What we'll be plugging in, I'll say, quote unquote, plugging in to our linear algebra version of functions are matrices, and the particular operation that's going to be involved is matrix multiplication. So the mechanics behind a linear transformation and a particular function are going to be different, but the idea is the same. We can choose a matrix to plug in, and once we do matrix multiplication, what comes out of it is a different matrix. And so there's this sense of input-output that happens when we work with linear transformations. And in the context of functions, our input would be the value of x that I randomly chose, and our output would be what the function produces once we plug the input in. Now notice that we plugged in a real number. -1's a real number, and what we got out of this function was a real number as well. Now this doesn't always work. Okay, you might know that there are some functions that produce imaginary numbers, all right, but we won't be doing anything with imaginary numbers in this course. But generally speaking, when you plug a real number into a function, you're hoping to get a real number out of it if you get an output. So let me allow that to sink in for a second for you guys, and we'll start to make the connection with linear transformations momentarily. So I'm going to present kind of like an abstract math version of what a function is. All right, so I'm going to give you the definition of a function. It's going to be presented in a little bit of a different way, and that's because there are some other entities that we need to blend in order to do a full treatment of transformations. So let's start with this. A function is a particular rule that quote unquote assigns each element of a set A to exactly one element, and this is key here, to exactly one element in a set B. So let's say, generically speaking, that we have an element A that gets assigned to an element B. So for instance, this -1 right here could serve as an element A in our real number version of functions, and the -1 is our element B. Then this notation, f of A equals B, indicates that we're assigning the element A to the element B. There's a particular term that's associated with the output that we get, and that term is called the image of A under the function f. So we add on another term for what we would recognize as the output, and that term would be image. Now, this set that you're collecting all of your elements in, that would get assigned to the elements in the second set. In other words, where we get these numbers that we plug into the function is called the domain of the function. Okay, so these consist of all the elements that are yet to be assigned. The set B, in other words, the set where these domain elements get assigned to, is not called the range, but rather the codomain of the function f. Now, sometimes the codomain will be the same as the range, but let's say that there are some elements of this set B that are not images. Okay, and I'll go ahead and clarify all this with the diagram below in a second. If there's any element or number in this codomain that the function does not assign an element of the domain to, then the codomain and the range are going to be different. Now, if you look at just the elements that have been, assigned something from A, that would make up the range of the function. So let me clarify all this with a diagram, and then we'll look at a function example from ordinary functions. So here I have a diagram from our textbook, and this is just a visual representation of our domain. And a function f has to take all of the elements or points in the domain and assign them to elements in the codomain, which this is a visual representation of that. Now we can already see that the function f is assigning the input A to the output or the image B. Let's say that there are some other elements, which we'll sketch those in. Let's do another point in here, and maybe let's allow the A that's already written to be A sub 1, so that we can call the second point A sub 2. The function f is going to assign A sub 2 to something in the codomain. Might not be the same element B, so for that reason, maybe I'll allow that B to be a B sub 1, and the element that A sub 2 gets assigned to can be called B sub 2. Get one more point going in the domain. Let's call it A sub 3. And let's say that the function f assigns this to a different point in the codomain, which we'll call, as you might expect, B sub 3. Now, all of these elements in the domain are going to get assigned to elements in the codomain. But let's say that after all that has happened, we only see the points inside this little blob I have here as images. So in other words, let's assume that the function f doesn't assign something from the domain to any of this part of the codomain. Is this making sense so far? So let's say that all the images are just like a little subset of the codomain. This subset in which we have all the images of the function, that's what we refer to as the range. And the codomain is the largest possible set that can contain such a range. Okay, so maybe let's make a note of that. The codomain is the largest possible set that can contain the range. Any questions so far? All real numbers, that'll be dependent upon what kind of a function we're working with. So in the next example, you're definitely right. The codomain would be all real numbers. In the context of linear transformations, our outputs are vectors, so our codomains are going to be different n spaces. All right, so if that's still kind of foggy for you, let's look at an example where we're dealing with a familiar function, f of x equals the square root of x. We're going to determine the domain, the codomain, and the range of this function, not necessarily in that order. And one thing that'll help us do that is maybe by looking at the graph of this square root function. Let me draw a coordinate plane here. You may recall that the square root function starts at the origin and then it just kind of hooks off slightly to the right while increasing up to positive infinity. So this is the function f of x. Over to the left, I'll write out a little list for all the things that are requested in the problem: the domain, the codomain, and the range. Let's start with domain. Okay. The domain consists of all the x values that can be plugged into this function. Okay, so keep in mind our function is the square root of x. Based on the graph, since this graph starts at the x value of 0 and then continues on, forever and ever to the right, our domain would be represented by this part of the x-axis. And we could write out those numbers using interval notation, and it would be bracket 0, comma, infinity. Now, before we do the codomain, let's look at the range. Okay, the range consists of all the y values that are produced by the square root function. Can anybody maybe offer what the range of this function is?
Is it 0 to positive infinity?
Yep, you got it. The smallest y value is at the origin, and we get y values that just keep on growing larger and larger in positive size. So visually speaking, the range would be the positive part of the y-axis, but also include the origin. So this would be our range. So it'd be bracket 0, comma, infinity. Now, the codomain is the largest possible number set that could contain the range 0 to infinity. Okay, so let's think of the largest number set, excluding any imaginary numbers, of course, that could contain bracket 0 to infinity. What's the largest number set that can contain that? Exactly, all real numbers. And there's a piece of this diagram that gives us a visual representation of the codomain, and that would be the entire y-axis. That would be our codomain. So this is an instance where the range does not equal the codomain. Okay, the range is only a certain subset of the codomain, which is why in the diagram above, I tried to indicate that sometimes the function won't hit certain elements of the codomain, and that's a situation where the codomain and the range are different. In other cases, the function will assign values to everything in the codomain, in which case they're equal to each other. Okay, but again, just think of the codomain as the largest possible set that can contain the range. So for instance, 0 to infinity, the largest set of numbers that contains that, excluding any imaginaries, would be all real numbers, negative infinity to positive infinity.